Mosel has been around for close to 25 years by now, and we have been building out the parallel and distributed computing features over, almost 20 years now. And so it felt right about the time that we actually go back and give an overview on what we have. I mean, even the latest release has added some features to this universe, let's say. So this is all putting many of the features together, and what we keep adding over releases to this set of functionality. But let's start with actually what we have in terms of parallelism in FICO Xpress. So we actually have two sorts of parallelism. We have the built-in parallelism on the solver level, meaning you just toggle a couple of controls and then the solver runs in parallel. And we have user-defined parallelism, which is the subject of today's talk, which is on the model level. So for the solvers, we have parallel dual simplex, parallel barrier, crossover, and then for the tree search, for mixed integer, and then also for constrained programming and also parallelized heuristics. There are lots of these features with different controls, but that's really not the topic of today's talk. It was just meant to mention this. For Xpress solvers, everything about parallelism happens on the same machine, so only where you're running, so it is not across networks, contrary to what I'm going to show today for the model, what you can do on the model level. For solver APIs, you can use the operating system multi-threading capabilities also to implement your own concurrent or even distributed functionality, but usually this involves quite a decent amount of programming on your side, and Mosel provides a, let's say, convenient layer, or actually several layers, as we will see, on top of this, and to make this reasonably easy to implement your own parallel or distributed computing solves, particularly for optimization problems. Well, I said the solver has automatic settings, but when do we need more? Well, when one case, for instance, production planning, you have sometimes very difficult problems that combine several types of sub-problems, and each of them is already difficult, like lot sizing, machine assignment, blending, sequencing, scheduling, load balancing. So often real-world problems combine many of these, and then it just becomes too large to handle as one monolithic approach. Another case may be something like marketing offer optimization. If you have millions or tens of millions of customers and thousands of offers, I mean, this just multiplies up, and you have often billions of decision variables, which again is beyond the what current solvers can handle in one, and you again need to work on your problem. Well, what you can do by a faster machine, well, it helps you to a certain extent, get it better on your solver. Tune the solver is usually a good idea for if you have a set of instances. And then also working on your model. And I mean, there is really what we're getting to today. You can try to simplify to aggregate, and then you can try to decompose either sequentially or in parallel. And of course, also try and see whether there is some other solver or solution method that helps. But I mean, here today, I'm really interested mainly in the decomposition and then resulting parallelization schemes. So breaking down large optimization problems into more manageable sub-problems, and then solve them either sequentially or in parallel. Now, for schemes, you have various possibilities. Straight away, just set your solver to run with different configurations and have these talk to each other while they're running and exchange updates on the bounds, lower upper bounds, I mean, solution values or the bounds, for instance. Then formal decomposition schemes, column generation, or cut generation. And I'm going to talk about some of these, but not all in today's session. Now, we really get down to what we have in terms of functionality from Mosel. Mosel is a language developed and created by FICO. It is a modeling language that at the same time has programming language functionality, so that you can write your models and solution algorithms in a single environment. The architecture is open, so we publish on the C level how to add new functionality in terms of dynamic libraries, DSOs from Mosel, how to add such new components into the Mosel language. The language is compiled, and that differs from many other offers. What you can, so it is like Java, you have a virtual machine, you compile your model source to a binary format that will be run on the virtual machine, portable across platforms, so you can develop on Windows and deploy this binary file on a Linux machine elsewhere. The binary format protects your intellectual property, and so it actually is suitable for working in a remote setting. Now, what we are talking about today, solver modules, mainly the Express solvers, so XPRS and XNLP, and then underlying the MMNL provides the handling of nonlinear expressions. We have a generic solver module, so not specializing Express, but connecting to any solver that supports the NL format, and then also Keras for the constrained programming solver. Well, we can handle multiple problems. That's a feature of the Mosel language itself, but it is implemented by these solver modules. And then what we're going to hear about a lot is the module jobs that provides most of the parallel and distributed computing functionality. Well, what I call the multis is the multiple items handling in Mosel. First of all, multiple solvers in a single Mosel model. So we can implement algorithms that combine solvers, for instance, the Express optimizer with constrained programming from Keras. Now we can have sub-problems. So we always have a main problem, and then you can create additional problems directly within a Mosel model. We can have sub-models. So within a Mosel instance, several models running, where there's one that is in control, the main model, and then a set of additional models in different files compiled separately. And then we have multiple instances or multi-node. So there we have Mosel instances, could be on the same machine, but typically on some remote machine. We just refer to it as the remote instance, even if it is also on the local machine. But we don't really care where the remote instance is located. Within there, we have models. If it is started from remotely, then submodules. It contains problems. Okay, but not just the basic concepts. And now we are going to dive deeper into this. By the way, if you have any questions at any time, feel free to add this. Type your question at the chat or in the Q&A window, and we will try to react if we can. Well, pneumonia jobs. It provides functionality for loading several models in memory and execute them concurrently. Well, not just executing them, but actually you want to control them. So it provides synchronization mechanisms and mechanisms for data exchange between models. Well, how does this work? As a user, you start a Mosel model just as usual. And from this Mosel model, you compile, load, and run a submodel. And this feeds back its results into the main one. Now, as you can perhaps see, it's a bit dark here, there's an error. Well, the arrow is going here from the submodel there, but there's also an error here. So there's important is meeting point waiting for termination. So that your main model actually waits for the submodel to perform its tasks and then processing the results. This can be as a loop, of course. So once we have processed results, perhaps we start the submodel, or we can have a number of submodels running in parallel, either copies or clones of the same, or distinct models. And then, of course, there also we can have a feedback loop. If some submodel comes back, the model might broadcast the information then to the other submodels that are running, and they treat this information correspondingly. Okay, so that's what we can do. Now, how do we go about this? Well, first of all, we have a new type for the Mosel language, which is type model. Unfortunately, we already had the keyword model and model that marks the start and end of a model. So now just to make it distinct, we used an uppercase M. So this is populated by loading a bin file. Now, running Mosel means we first compile source file mos to BIM. Then we need to load the binary file into Mosel memory, so parse it, so have it ready to be run. And then we run it, which instantiates the Mosel model with actual instance data. And we get an additional step. Now, if we are running in this context here, we have wait. Because if we do not wait, our main model that has started a submodel will just go on processing because the other one is started concurrently. So there is no automatic putting it on hold or pausing the main one unless you actually program this. So compile, load, run, and wait as the sequence here. And well, wait means that the current model sits and waits for a message or an event from the submodel. So here is the basic sequence, compile, load, run, and an event here, we're just ignoring it by saying job, next event that we have received. Well, what is an event? Event is a message that has a class, which is an integer value, and an attached information, which is just a real. And the integer actually means, well, it's like a code, integer code, meaning, but that has an agreed meaning between the main and any of its child models. So they, of course, need to agree on this. The only predefined one is event end, which is a set constant, and then you can use other values to create your own classes of information you want to communicate. Exchange always between a model and its direct parent or child. So no jumping. If you have several levels of imbrication, from 2 levels down, you cannot send anything directly up by several levels, for instance. Managed in a first in, first out queue. Well, event class, again, uppercase we have chosen here to be consistent with the uppercase M. And so you have the class, the value. And this is not to be confused with the exit code. So if you're running a Mosel model and you have an explicit exit call in your model, for instance, to signal some error situation, then this is captured by get exit codes. And it's different from the events that can get sent. Now, that's starting models, but what you're really interested is the exchange of information between models. And so we have data exchange between concurrent models, specific functionality to extend models' data input and output mechanisms, particularly for working in memory. And these can also be used for synchronizing the model ones. So here, one form is the shared memory driver, which is, you can just think of this as a block of data that gets written into memory. So you write it out from a model or read it, exchanging between a model and the Mosel instance where this is stored. Or you have a memory pipe. There, the receiving model first needs to open the pipe, and then other models can write into it. So it actually, the receiving model is going to be blocked until it receives something in this pipe. So that's a synchronization mechanism. Well, once more, shared memory. It's a generalized version of the mem driver that we have for the basic version of Mosel. And a couple of utility routines, and there was saying, this has really just been introduced with the latest version of Mosel, have the shared memory, this asterisk form, deleting everything that is in shared memory and reporting on the size of information that is stored in shared memory. We have chosen not to have any more detailed reporting on shared memory contents just for security reasons, so that you cannot inspect what other models possibly have written into Mosel memory unless you really know what is the name of the label you want to read. Okay, and the memory pipe, this is sending data through a pipe between models, also with some utility routines. Now, let's come to our first example. Just as an aside, All the examples I'm presenting today are actually part of the Express distribution. So if you have got a recent Express installation, you should have all these examples already on your machine. But given the large set of material that we are providing, you might not actually be aware that you have this information. Now, machine assignment and sequencing. We want to produce different products on a set of machines, but these machines have different characteristics. So they have, for doing the same job, different processing times and possibly different costs. And then we have release and due dates per product. What we need to determine is a production plan that minimizes the total cost. So we have a machine assignment problem. What goes where. Then we have on every single machine the sequencing of operations. The assignment is better formulated as a MIP model, and the sequencing is easily implemented as a constrained programming model. It can also be implemented as a MIP model, but at least for the example we have run, the CP is faster for this type of sequencing decisions. Okay, so what does it look like? I have two files. I have a Mosel model and I have a sub-model, which is the constraint point model. Now, from the Mosel model, I start my optimization. So here is, I'm starting the optimization solver, so Express. And at predefined places, I'm using the callbacks. So this is, of course, implemented in C, calling back into Mosel to have some user code is executed here, and this will be actually then prompting the execution of these submodels to see I have an assignment of jobs to machines now. Can I complete the sequencing within the, to match the release and due dates for jobs that I've got. After the submodels are done, I have a callback. I finish my callback, and if it didn't work when completing this schedule here, then I'm adding a no-code cut, excluding this combination of assignments, and the optimization goes on in my MIP model. So here we are in the case of the multi-solvers and multi-model, so separate model files. What this looks like. Well, I've got a MIP model. I'm not going to go into detail. What I'm interested in here is I'm setting a callback for Express Optimizer, and the implementation of this callback function is actually then generating a calling for the different machines. This generate cut calls then once the CP model. I've not shown it on here, but I mean, here the counter says whether we have added cuts or not. Okay. Just taking a step back at this point, I jumped immediately into this algorithm while we have MIP model, CP model, and so two different models running concurrently. We can also, within the Mosel language, use the MP problem type to actually have separate different models in the same environment. So here, what we do is the type MP problem, and then with MP problem do, and within this block, I'm now in this new problem. I can, given that this has a name, I can come back to this problem later on. So work with one problem, define it, perhaps solve it, and then also switch between the solution values, for instance, of different problems. Decision variables can be used across several problems, but constraints are always created within a particular problem. So I can have solution values, different solution values for a variable within different subproblems. An example here, we have the job shop problem. So here this is for printing wallpaper that have different color schemes, and so they have green, blue, and yellow printing, and they run in different orders through the different machines. And of course, the machines process one job at a time, and once when the wall of paper is running through, it cannot be interrupted, so non-preemptive. What we could do now, just as an example, is to solve the single machine sub-problems while sequencing tasks on a machine, and try whether this partial solution information, just a sequence for one machine, can actually help warm starting the optimizer. And so I have two distinct problems, a sequencing and a job shop problem. So here I'm in this case, well, all in one, so several problems, but within the same model. So implementation, we say with the sequencing problem, I'm running, but here I'm just have this in loop for every M, so for every machine. I'm doing this separately. I'm saving the solution information, and then what I'm doing with this, well, that's just a partial solution because it's just for one machine, but I'm just populating this information and adding this as a MIP solution, and I'm telling the solver to try to make good use of this solution. But that's just showing this. Well, actually, this is what I've opened here is the scheduling I have mentioned previously. So that was, I can run this here. And but here I have, this was the version with a MIP CP. And here I have a MIP subproblem. So here the time was 1, and I'm actually, no, and I'm sorry, here the time was 1, and while not solving in parallel. So now I have the MIP and CP running in parallel. So I'm starting this one here also. The total time is also 1. And the same one for the math problem. So MIP and kind of doing the same node numbers, but here these subproblems are slower. So we are in the same range of node numbers. So here I'm getting always to the same results, of course, but the subproblems are slower for this case. Okay, so now coming to my job shop problem. And here I have exactly what I've shown previously. So I have my sequencing of problems on the machine, and it's running through. Okay, so what I wanted to show is actually I have my start solutions that are processed. And here it actually tells me that some of these solutions that have been loaded, the solver has been able to actually complete it via local search to a solution. So we start off our, even just the root node, we start off and we already have a solution. Not a good one, but at least we have a solution here. Okay, and this can be parallelized. So here this was the sequencing, and we have the panel version where we load this as subproblems and run everything. So here again, all these examples, I've just opened the examples distribution, example/Mosel from the current Xpress installation. So these example files are all in there. Okay. Yeah, let's move on. Now, as I said, this is what I've already shown. I can either have these subproblems, then they are solved sequentially, or if I put them into separate models, then I can run these submodels in parallel. So I have either this one here, all sequential, because I have everything in a single model, subproblems, or I have separate models, and then I can run this completely concurrently. So that was a bit too fast. So here once more multi-problem and multi-model, the difference. Well, what I'm saying here, multi-problem, problems can share data. And for multi-model, in general, I need to communicate data in memory via the Mosel instance. Now, that is not entirely true in all cases, because we have actually, well, not so long ago, added the possibility to clone Mosel models. So what we've seen so far, it was always the compiling possibly only once, but then load and run for every single submodel instance. Now, what we can actually do once a model is loaded in Mosel memory, I can just take a copy of this, a clone of this already passed information, and just create a clone in Mosel memory out of this. Either for a BIM file, so a submodel has been loaded, or a model can completely clone itself. And here is just a test. So what is the effect? I've taken two fairly large model files. I don't know, the large one must have several tens of thousands of lines. I don't have the measure at hand, but times measured here is just for loading the model. So not processing in it anyway, it's just the loading. So the Mosel parser reading in this file. And I mean, doing the first one is of course the same, but then for the standard one, if I'm doing this over and over again 10 times, we have a total measure here and also memory consumption. Well, for this first file, if I just clone, while the time is shorter, times are very fast here for the file size we're talking about. So usually it's really negligible as opposed to solving times for optimization models. But I mean, you can see for the larger model, we actually, through this cloning, we do have a gain in terms of memory usage, although it's just a standard model. So, but there's still somewhere structures or information that quite apparently can be shared by different clones of the same model. So Mosel is doing less work, and it uses less memory for these submodels. Now, these previous measures were just standard models, nothing particular marked up for sharing. Now what we can actually do, we can share data between clones. And well, there's an indicator of what is shared at a certain point of time. What we have seen so far was we have a file, and well, it populates a model, and then a submodel in another file, and shared data via the IO driver shmem has been written out to Mosel instance memory. And so each model that needs the data, this data for processing, actually needs to take a copy into its memory space. This works also, which is something we're going to see a little later on, across Mosel instances. So I can reach from one instance the shared data that is stored on a different Mosel instance. But if I'm running on a single instance with cloned models, we actually can have shared data that is a single copy. A single copy lives in a model and in its clone at the same time, but they actually use the same data here. So there is no copying happening at all. And given that we are not copying, if I mark up this data now, this keyword shared, I'm loading. Here you see loading. It's not using any name of a Vim file. That means just the model itself is duplicating itself. And I'm either using sub with false, which is default, or I'm sub with true to start the submodel one here. The default is, well, I populate my data, and then I'm node 1 and waiting for the submodel to finish. In this one, I'm going to start the same thing again, and I'm going to enter here. So I'm actually modifying this array A, which belongs to both of the, because it is shared. And so you see, after I'm done, the values of this array in the main model instance have changed. What is the use of these things? Well, quite often, you might have some computational expensive task, for instance, in data pre-processing. And so you could profit from spreading this, so parallelizing this effort. And just by having several versions of these clones of the same model running to perform this task. Of course, here, for instance, I have input data and then I have a result array. So they would work right into different pieces of the result array, just the results of some expensive calculation. Here, I assume I have the primary model, that is number 0, and then I'm starting 5 submodels here. And if I'm not in the main one, then I'm actually performing the calculation. Okay, so the main one reads data into shared memory, and then it starts running these clones. And the clones, well, they are just doing this one, doing the calculation, and each of them is writing back into this. But here you see the M, so they're actually writing back into different areas of the same data structure. But there's no copying whatsoever. Okay, now taking this one step further. So far, we have been living within the same Mosel instance. Now, if you want to do this remotely, so we have a local instance that will be in control and starting model ones on the remote instance. You're going to have the same communication mechanisms, so starting submodels, and then the event mechanism to coordinate and synchronize. So we have a local model, Let's start, say, remote submodel 1. And now, well, where to put data? Well, it doesn't really matter. I mean, the data input files and so on, they live wherever this is convenient for you. They could be with the local copy, they could be with the remote one, or they could be in some, for instance, in some central repository. So all these possibilities are feasible and can be used with Mosel. So what we need to do in addition to what we have seen so far is actually a new piece, that is the Mosel instance management. So actually we need to reach out, well, start possibly and connect to the remote instance of Mosel. For this purpose, we have again new I/O drivers for reaching the remote instances, and then well, to connect, and then well, for accessing physical files, then the IMT for remote, well, as a prefix to other drivers. Now, we had our compile node run wait sequence, and now we are adding one more, which is connecting to another Mosel instance, which is specified by a machine name, by an IP address, so whichever is working for identifying the machine you want to connect to. We have the option to use perhaps moving back, using protocols like RSH, or we can use XSRV, which is the Mosel server. If we decide to use the Mosel server, then it needs to be started with a small program called XPRMSRV. It needs to be started on the remote machine to enable it to receive requests for running Mosel remotely on this machine. There's a configuration file that might already be familiar to you if you have been working with Insight, in particular versions up to Insight 4, where this was the main configuration for Insight. Well, not all of this here, but just saying where there are different options in this configuration file that you can reset. Refer to the documentation to actually see what you can do. If you just want to do tests on your local machine, while you can leave the string empty, then it is performing this command here. If you put localhost, then you need to have started XPRMSRV, sorry. Or you can say with the asterisk, you just ran exactly in the same Mosel instance. Okay, so that was we had previously, compile, load, run, wait. Now we add a connect step, and we can actually choose keeping the compile locally, then connect and load this from our local machine into the remote one. So actually now here this load is on the remote machine, so this BIM file is actually remote for it. So we need to put the prefix onto this one here to get it from the main node, the primary one. Running doesn't change at all because it is just the model that I have loaded. Or the other way around, I'm connecting and compiling on the distant machine. Well, depends again which one is preferable, depends on exactly what you want to do with the application. Now, all the documentation about this is on the publicly available, in particular the Mosel Language Reference Manual chapter Jobs, and then the white papers, multiple models and parallel solving with Mosel, and the mixed MIP CP example was from the white paper Hybrid MIP CP solving. Another example is also discussed in the advanced evaluators guide. Okay, but as I said, if you have any questions, please jump in. Now moving on to yet another extension of this, which is XPRD. Now, we have been completely in the Mosel world, but now if you want to embed your Mosel models into some bigger context, what to do? So we have the possibility to start Mosel models from a locally running Mosel model. What we want to see now is actually, what if I have something else? XPRD is a library that is available for C and Java. And I guess in the, so here, this is what we've seen so far, my local instance controlling a remote instance. Now, instead of having a full Express installation with Mosel running here, we just put a C or Java program, XPRD, using XPRD library, nothing else of Express, so completely disconnected, no license, required whatsoever on this machine that controls the remote executions. Same commands as what we have seen, and it also supports the event signaling system. So the communications for the Mosel models, the submodels that we are controlling via this mechanism XPRD, they just remain exactly the same. And so here, this is what we have seen previously with our connect, noding, disconnect. And now we have a Java program doing exactly the same. Well, the only thing that we need to add is actually, first of all, initialize the XPRD instance, but then we have exactly the same commands: connect, compiling, noding, executing the model, running, and waiting for its termination, and then, well, disconnecting from the remote instance. So now we have just a small piece of Java code and only a single library to be installed locally to control whatever is running remotely. This is actually a technology that is underlying Xpress Insight. So Xpress Insight is using the XPRD Java to control the execution of Mosel libraries. This is not to be confused with the standard Mosel Java API. So here we have XPRM. This library is part of the standard Xpress installation. Well, we have the compile, load, run, but you see there's no wait, because here we actually we are not running concurrently, we just wait for the run to terminate before our Java program goes on. So that is not the topic of today's call at all. This is just standard embedding of Mosel models into Java. Well, use cases for this. I mentioned that Insight is relying on this functionality, as does Workbench actually for executing Mosel models. What this does is you separated optimization tasks into separate processes. So, well, this means, for instance, you could limit the amount of CPU memory that is available to such a process. And also you control applications from an environment. For instance, you could run Java, but perhaps Express itself is not available on these architectures at all. Okay, an example here of remote solving, again, present in the distribution. Idea is, if we have a traveling salesman problem where we have a large number of nodes that need to be visited, and each of them exactly once. While that's a difficult combinatorial problem for MIP, while we can move up for exact solving, we can move to the order of standard optimization tools. So not talking about special algorithms, we can move up to the area of about 100 nodes to find the optimal solution, just throwing it at the standard MIP solvers. But if we want anything larger, well, we need to move over into heuristics. And one idea would be here, well, if I can group nodes geographically, well, calculate a tour geographically in some area, and then unfix those that are in the bordering region and just keep those fixed that are likely not to be touched by any changes. And solve a partial problem that includes just a subset of these nodes, and then I get a new tour where these two are glued together. And do this recursively for neighboring subproblems until I've solved my entire problem. Of course, the resulting solution is just going to be a heuristic solution, and I probably don't even have any possibility to estimate on the solution quality, but I can obtain the solution relatively quickly. But here I have in the distribution, it's a TSP problem with a bit above 300 nodes. And if I run this one here, so what you can see here in the output, and I mean, that's the most important piece, is over time, what we're doing here is getting bigger and bigger. So we start off with small subproblems. You see here these subtours, and then we start gluing together. So these lines become longer because we are merging the subtours of my neighbors. And then the final one is here. The last one is, of course, the biggest, where we have a result. Okay, and of course, all these subproblems, they are independent, those that are on the same level here. And while also this P1, 2, for instance, the merged one is independent of P3, 4. And so we can solve all of them in parallel on as many nodes that we have available locally or on our network. Okay, now we've been talking about networks, and well, the Mosel communication mechanisms are not the only thing that we can do, and while a common format on communicating in networks is actually HTTP. Mosel supports HTTP commands. A Mosel model can act as client or as server to HTTP. So here, this is the case of a client. I'm just sending a GET, and well, C, for instance, retrieve the product matches, retrieve a web page. I have status codes for HTTP status codes. Some of them are predefined, so we can actually interrogate what is their meaning. I can use synchronous or asynchronous mode controlled via a parameter. Synchronous means I'm waiting for the reply, my request to come back. Asynchronous is I just go on and treat the results whenever they arrive. So as said, the model can act as a web service by starting an HTTP server. In terms of functionality, whether it is now a server or a client, we have these HTTP requests. We also have ways of creating JSON files, so encoding data into JSON format to send them along with standard HTTP queries, be it to a Mosel server or to some other tool that actually expects HTTP requests. So here, example, I'm creating a tar, and then I'm actually including here the assumption is I have a Mosel server running that expects some data, some input, and provides some output back. Okay, so here the server would look in a very reduced version like this. And what we see is actually there are lots of common features. So it is overlapping with what we already have seen for jobs. So we have still the notion of events to coordinate this, special event type for HTTP queries, and sending back things. But here the communication mechanisms for implementing this server are what we have already seen for jobs. But of course, the protocols behind are different. And so there is an important, interesting feature here. When I'm starting a model as a submodel from a Mosel main model, they remain connected. If there is a network failure in between, the entire execution stops, fails, so I've lost my submodel. If I want to be protected from this, I can actually decide in the submodel that I'm detaching it from the one that has, from the parent that has started it, and it becomes independent. But of course, I still need some way of reaching out to the parent model. So what I can actually do is switching over from the connection that is now broken between the main and the parent and the child model. This Mosel connection is broken, but I can switch over to communicating between the two via HTTP. In this case, of course, the main one needs to have an HTTP server, so needs to be able to receive the HTTP queries that are sent by the submodel. And so here what we have is a possibility to implement fail-safe distributed optimization applications, because we no longer suffer from everything breaking down if there is a network failure. In this server, while we have functionality to implement HTTP servers, and there's also a special way of cloning these servers. Actually, that while one server treats one incoming request at a time, we could create clones of it that share the request queue, and then each of them takes incoming requests from the queue and handles them. The full example of this one is printed and documented in the Mosel language reference manual under the HTTP chapter. Talking about HTTP, we usually want to use a secure setting, so actually HTTPS. For this one, we have the Mosel tool and also a Mosel module. But here I'm interested in the command line tool, MMSSL, that I need to use to set up first, and then we can, while we get a set of certificates and also a key pair generated, you can call this setup repeatedly. It is not going to override any existing information if it has already been run. Okay, so this is really if you want to have a secure connections, if you want to have a secure HTTP server. Okay, small example, Mandelbrot. Well, Mandelbrot actually is a formula or a set of formulas, and what you do is you calculate the color of pixels depending on whether some iterative algorithm terminates or not. If it did not terminate, then this is black. So that's 1 up to time limit. So if you have a lot of black in some Mandelbrot picture, then actually this is slow because the black means 1 up to the time limit. But a bit of black is medium, and then no black at all means this terminated earlier, so I just got some color. And so here, my example, that's again in the set of Mosel examples that are present, and I'm starting this one here, and sorry, I should have stopped this first and running this again. So what this does, actually, it brings up a web page, and here I'm starting this and I'm running my Mandelbrot. So here the black, as I said, takes a bit longer. So here I have to stop it and I start with some other configuration. And this is built in the model, what is the configuration of the parameters of the Mandelbrot formula. And I can run this. So here my Mosel model has actually exchanged information with the web page. There's a bit of JavaScript involved on the web page actually, that I've started to exchange information between the web page and Mosel, but all this relies on commands on the Mosel side, so using the MMHTTP functionality. Okay, so as I said, also present in the set of examples. And now coming to a couple of tools. Well, what I've been telling you might have sounded horribly complicated, in particular now if I need to reach out to distant machines. So what we have actually done, we have created a package called job queue that sits on top of the jobs in order to ease the implementation of distributed applications for you. So I have a notion of jobs. This is the models I want to run along with their data or any other required files. Then I have task queue. So these are the Mosel instances that just receive requests for running instances. And then I need a set of controller programs actually to monitor what is happening, just to be on the safe side. So I'm not just simply starting something remotely, but on this remote node, I actually have a watch job that manages what is happening there, and then also some reporting. So what you have as a user is a Mosel model that uses the job queue. Now, this one starts invisible to you, a scheduler, and this scheduler has workers. So these are the job queues that we have on the, either locally or on remote instances. And the scheduler starts controllers. So that is completely invisible to you. What you see is actually, or what you configure is the Mosel models along with data that you want to run in these instances. Well, how do you go about this? 4 steps. First of all, you have your nodes. So as I said here, either these are local, and that's localhost started with a different protocol, or then some machine name here, machine name or IP address to say, well, it's on a different machine. Secondly, I'm defining my jobs. I can start a job by providing a BIM file. I can define a job as a Mosel file, and I might add data files, or here say I want to retrieve a result file with this. And I have a third job, which is just a model. But here I'm saying, well, I want to do 2 attempts if for some reason the execution fails first time. Now, I'm starting jobs by assigning them to an instance. So I have my queue, which was step 1. I'm putting jobs into this, and with this I'm creating a task that is now on the queue. And by putting it onto a queue, its execution, if this instance is free, will immediately start. And then I just need to wait for these queues to finish, or well, get the next. So I can also just sit there and monitor, and what comes back from a queue is what has been executed. Because as I said on the previous screen, well, I can dynamically add jobs, those that are first already starting, and I can just keep adding things, and then I'm sit there and wait for the results to arrive, and some reporting via some predefined statistics output files. And this was I had specified a result file, and here I can see exactly what has been written into this by the job. This entire module is available on the public GitHub for Mosel. So we have the source, and if you type Mosel make doc equals true, then you're generating its online documentation directly out of the source. Another tool that I want to mention, without going too much into detail, just to say that's another way of easily running Mosel models in parallel, not particular for testing. This is Mosel test. The binary Mosel test executable is included in recent Express builds. What this does is you have files in a subdirectory specified via source dir. Can also just be a single file, but if you put a subdirectory, it is going to run everything that it finds under this subdirectory completely. But all subdirectories and at any levels it finds under this location. And not just Mosel files, but also C and Java files for Mosel. And well, why I mentioned this here is actually you can specify workers, and you just say, parallel workers, you put the number of workers to something larger than 1, and then it will just run your Mosel programs that are under this, let's say default all test location. They are going to be run in parallel, unless you have used some special markup. If you have a sequence of tests that absolutely need to be run in parallel, then you can mark them up, and they will be excluded from the parallelization and be run in sequentially. Nice feature of Mosel test is that it provides also output for coverage reports, and so you can actually use this to test and report on the coverage of any Mosel apps that you have written. But these are, of course, external tools, but we provide reports in different formats. Again, this is also the source form, can be downloaded from GitHub, but the executable is indeed included in Express builds, so you can just use it straight away. Okay, well, with this, I have reached the end of today's talk. So we've seen the Mosel distributed framework, a really quick walkthrough of the functionality, also talking about XPRD, so the library version, and HTTP, and then the tools, job queue, or the parallelization features for job queue for writing your own apps, and the parallelization features of Mosel test, along with a number of examples, non-exhaustive. So I've just used a selection of examples from the documentation that you can find online. So here, in particular, the Mosel language reference menu chapters, jobs, and HTTP. And then the white papers, pilot solving with Mosel, and the one about hybrid, MIP-CP solving, and also the XPRD reference menu. Examples in your Express installation, everything I've shown today, or online in the online examples database, and then the public Git repository once more for downloading features. Well, with this, I'm closing for today, and I would like to open the space for discussion and any questions from the audience.
Thanks, Suzanne. We'll go ahead and start with the first question in the order that it was received. This is a 4-part question. The first part When launching models via the .NET API, is there any exposed functionality to submit directly to Express Remote Service from C# rather than having to create a parent Mosel model and pass all parameters through it?
From .NET, actually, we have something else that I did not cover here, which is called executor, and this is a portion actually of Express Insight. So if you want to launch anything remotely, you need to have a server on the remote machine listening to what you're doing. So yes, if you have executor, so this portion of Express Insight running to listen to you, you can configure Express Optimizer, so just when running matrices, so from the library level, and that is available from any library API of the solver, you can configure it to actually connect to remote machines to run your matrix. But the remote machine needs to have an Express installation, and for this functionality, not just Express, but actually the executor.
Thanks, Suzanne. Following up on that, when launching from .NET, we can bind input and output streams to a model. This doesn't seem to work if we use distributed computing. Are there any plans to expand the functionality?
Well, for .NET, we are not providing the XPRD version for .NET. So this is only for C and for Java, and actually internally for Workbench, we have the JavaScript or TypeScript version. So for .NET, we are not providing this. Right now, we are not planning this, but we could take this offline and discuss the needs for this.
Thanks. And then the last part of that question, there are already functions to set an affinity mask. Do you have any recommendations on using them with newer P-core/E-core architectures? Specifically, how to detect which cores in a mask are P versus E when automating across different machines rather than hard coding masks for hardware configuration?
Yeah, we presently we don't provide any specific functionality for this. Also, the Express solver actually it just takes whatever is available in terms of course. So there is no way of pre-selecting where exactly or which portion of the machine to run this on. The only settings we have for this solver is actually to limit the number of threads.
Thanks, Suzanne. The next question, is Mosel model a mixed integer program of the master problem or the entire optimization problem? I think the question rephrasing is asking whether the Mosel model in the first example you used is the master MIP in the distributed setup, or whether Mosel's modeling the entire optimization problem end to end.
I think this is so that is probably referring to this one here, where we have the scheduling problem, and here we have indeed just a partial problem in the MIP. So it only has the assignment problem, and we're actually in a sense abusing the cut generation functionality to, well, not adding cuts, but actually proper constraints via these no-good cuts from MIP. So that's additional information that is not present in the MIP model to get the sequencing aspect into it.
Thanks, Suzanne. And last question, on the shared memory for problems, we were previously recommended to communicate via files rather than memory for performance. Is this still the recommended approach?
Depends on your systems. I mean, the shared memory is memory. Well, it's information that sits in memory, and then this memory is not available for your solving. So if you have large memory blocks, and this is why we've introduced recently also this inspection functionality for shared memory, if you really store large amount of data in shared memory, well, this is space that is not available to the solver. And so, I mean, if this becomes really large, but better store it into files to free space for the solving. Or, I mean, there's also the FTD that I've shown. Once you don't need the shared memory block anymore, delete it, perhaps even before you start the optimization one.
Excellent, and that rounds out the questions. So just want to thank Suzanne for an excellent presentation, and thank everybody who took an hour out of their day-to-day to come to this FICO Xpress talk. Thank you guys. We'll go ahead and conclude the event, and again, appreciate your time, and thank you for your participation.
Bye, everybody.